Hi students, welcome to my channel Thoughts of Physics.
In the video series of oscillations, in this class I am going to explain energy of a particle in simple harmonic motion, that is the total energy of the particle executing simple harmonic motion. Now the total mechanical energy of the particle is equal to the sum of kinetic energy and potential energy. If we want to get the total energy, we have to find kinetic energy and potential energy of the particle, and we have to add the two, then we'll get the total energy of the particle. Now let us find the kinetic energy of the particle and potential energy of the particle individually, and then after that we will add the two to get the total mechanical energy. Now, so first find the kinetic energy of a particle in simple harmonic motion. Now, so already we know that the velocity of a particle executing simple harmonic motion. Whenever the particle executing simple harmonic motion, the velocity of the particle expression is v is equal to omega into root over a square minus y square. In this formula, capital A is amplitude of the particle and y is the displacement, omega is the angular velocity. Now the velocity of this particle given by this formula. Now we know that the kinetic energy of the particle Ke is equal to half mv square. The kinetic energy is equal to half mv square, where m is the mass of the particle, v is the velocity of the particle. Now half m into v square. Already we know the formula of velocity v. Now let us substitute the value. V is omega into root over a square minus y square whole square. So v square. Now kinetic energy is equal to half m. So now the square can be applied for these two terms, omega square, and if you apply square for this, square root get cancelled, then we will get a square minus y square. So this is the kinetic energy of the particle executing simple harmonic motion. So kinetic energy is equal to half m omega square into a square minus y square. So this is the kinetic energy of the particle. Let it be equation number 1. Now, so now let us find at mean position and at extreme position the value of kinetic energy. Now at mean position the displacement is 0. When the particle at mean position, the displacement is 0 because the distance generally we measure from the mean position. So when it is at mean position, the displacement is 0. Then if you substitute y is equal to 0 in the first equation, the kinetic energy is equal to half m omega square, as it is we have written m omega square a square minus y is 0 at mean position. So y square means it is 0 square. Now the kinetic energy is equal to this a square minus 0 square is a square. So finally we will get the kinetic energy at the mean position is half m omega square a square. So kinetic energy is maximum at the mean position. This is the maximum kinetic energy. So Ke max means maximum kinetic energy, that is equal to half m omega square a square. Now this is at mean position. So mean position kinetic energy is maximum. Now at extreme position the displacement is maximum. So the displacement y is equal to a. The maximum displacement from the mean position is called amplitude. So at extreme position amplitude y is equal to a. Now if you substitute y is equal to a in this first equation, now the kinetic energy is equal to half m omega square a square minus y is equal to a. That's why a square minus a square. So a square minus a square gives 0. So the kinetic energy is equal to 0. That means at extreme position kinetic energy is minimum. The minimum kinetic energy is 0. That means the kinetic energy is maximum at the mean position and minimum at the extreme position. This is about the kinetic energy of the particle. Now let us find the potential energy of the particle in simple harmonic motion. Now generally the potential energy means it is the stored energy. Potential energy means it is the stored energy. So for example, if you want to displace the particle from mean position to a distance y, from mean position means y is equal to 0. Some distance y, if you want to displace the particle, we need to do some work done. So the work done in displacing the particle is stored in the form of potential energy. So to find the potential energy, we need to find the total work done in storing the energy. The total work done in displacing the particle from mean position to some position. So potential energy, if we want to find the total work done. So before finding the total work done, so first we need to find the small work done in displacing the particle by a small distance. So by integrating that small work done, we will get the total work done. So this can understand like this. For example, if we have 5 bags, so each bag it has equal number of balls, let us say. So in the first, let us say we have calculated 6 number of balls. So at a time we can't calculate all the balls in all the bags. We can't calculate all the balls at a time. So first what we will do means, we generally used to count. Generally we used to count the balls in one bag and multiplied by the number of bags. It gives the total number of balls. Similarly, if we want to get the total work done in displacing the particle, so first we will find the small work done. By integrating that small work done, we will get the total work done. The total work done will be stored in the form of potential energy. Because here we added this, all the balls in all the bags we have added. So integration is also same. Summation, integration, that is nothing but addition. In case of a continuous system, we consider integration. These are the discrete system. That means it is one particular bag and these are different bags. So these are the discrete. In case of discrete, generally we use summation, and in case of continuous system, we use integration. So now already we know that if you want to find the potential energy, we need to find the total work done, because the total work done is stored in the form of potential energy. So to find the total work done, so work done is nothing but W, that is equal to force into displacement. Force into displacement. So first let us find the force. So before that, already we have discussed that the acceleration of a particle executing in simple harmonic motion, A is equal to minus omega square y. And this is the expression for acceleration of a particle executing in simple harmonic motion. Now, the restoring force at any instant. Restoring force means the restoring force always acts towards the mean position. The restoring force always acts towards the mean position. Due to that restoring force, the particle try to move towards the mean position. So now the force formula F is equal to ma, m into a. We got this formula, a is equal to minus omega square y. So if you substitute that, we will get the restoring force F is equal to minus m omega square y. This is the restoring force. So this restoring force acts towards the mean position. But what we need to find, that is the work done in displacing the particle, that is stored in the form of potential energy. Potential energy, if you want to find, means the total work done in displacing the particle we need to find. So the force which is displaced the particle, that is the applied force. The applied force displaces the particle, not the restoring force. Due to the restoring force, the particle try to move towards the mean position. So the force which displaces the particle is applied force. So applied force and restoring force both are equal in magnitude but opposite in direction. Restoring force always towards the mean position and applied force away from the mean position, because if you apply some force, the body moves away from the mean position. So that's why the applied force, it can be taken as F is equal to m omega square y, because restoring force is minus m omega square y. then applied force is opposite in the direction, so it is minus of minus m omega square, that gives m omega square y. This is the applied force. Now, so to find the potential energy, we need to find the total work done in displacing the particle. So before finding the total work done, we are finding the small work done, that is dW. Here dW is the small work done in displacing the particle through a distance dy from the mean position. In displacing the particle through a small distance dy, that small work done is dW. So now dW is equal to F into dy. Generally the work done formula, product of force and distance, displacement. So that's why the force and displacement for this dW small work done, the small displacement is dy. That's why dW is equal to F into dy. Now already here this is the applied force, because applied force displaces the particle. So dW is equal to, in place of F, if you substitute the applied force, that is m omega square y into dy. This is the small work done in displacing the particle through a small distance dy from the mean position. Now to find the potential energy, we need to find the total work done in displacing the particle from the mean position to a distance y. So W is the total work done in displacing the particle from 0 to y. 0 means mean position. From mean position to a distance y, if we want to displace the particle, the total work done is W. So this total work done is stored in the form of potential energy. So the total work done, that is equal to integral dW. Integration of the small work done gives total work done. So now W, the total work done, is equal to integral dW limits from 0 to y. So what are these limits? Limits means 0. That is called initial point. That means we are displacing the body from mean position. So at mean position the displacement is 0. And we displaced the body to a distance y from the mean position, and the y is the final position. Initial position is 0 and final position is y. That means these are the limits. This is called lower limit and y is called upper limit. 0 is the lower limit, y is the upper limit. So integral dW, the integration of the small work done gives the total work done. Now W is equal to integral 0 to y dW. Already we have determined here dW m omega square y into dy. So now that dW we have substituted here m omega square y into dy. Here m omega square is constant. Now we have to take the constant out of the integral. So now this, if you take this m omega square out of the integral, it gives m omega square, and if you take m omega square out of the integral and we left 0 to y, y into dy. Here the variable is y. Variable is y. Actually this integral is in the form of integral x power n dx. Integral x power n dx is equal to x to the power n plus 1 by n plus 1. This is the formula of integral x power n into dx. That is equal to x power n plus 1 by n plus 1. But here the variable is y, and in place of n here 1, because y upon, so no value means it is 1. Y power 1 into dy. The value of n is 1. Now m omega square, as it is we have written, if you apply the formula x power n plus 1, the variable is here y. So y power n plus 1, n is 1. So 1 plus 1 over n plus 1, that is 1 plus 1. So limits from 0 to y. After applying the formula, limits we have written like this: 0 to y, where y is the upper limit and 0 is the lower limit. Now m omega square, as it is we have written. Now y power 1 plus 1, that is y square, by 1 plus 1 is 2. Y square by 2, and limits from 0 to y. Next we have to apply the limits. First we have to apply the upper limit, and after that we have to apply the lower limit. Now m omega square as it is we have taken, this is constant, and if you apply the upper limit in place of y, that is variable, here y is the variable, so in place of y we have to apply upper limit also y, so that's why if you apply y in place of y, it gives same value, that is y square by 2. And while you are applying the lower limit, we have to take minus because we are lowering the limit value, that's why minus. And if you apply lower limit is 0. If you take 0 in place of y, it gives 0 square by 2. Now this is the application of limit. First we have to apply the upper limit, and while you are applying the lower limit, we have to take minus. So now this we will get after the application of the limits. Now this 0 square by 2 gives 0. Then after simplification, the total work done W is equal to m omega square. This gives y square by 2. So m omega square y square by 2. This is the total work done in displacing the body or the particle from 0 to y. That means from mean position to a distance y. The total work done is W. So this total work done is stored in the form of potential energy. Now the potential energy is equal to half m omega square y square. This is the total potential energy, half m omega square into y square. Now let us find the potential energy value at mean position and extreme position. So as we have discussed in case of kinetic energy, at mean position the displacement is 0, y is equal to 0. Now if you substitute this y is equal to 0 in this potential energy, half m omega square, y is 0 at mean position, so 0 square. Now potential energy is 0. That means at mean position the potential energy is minimum, that is the minimum potential energy is 0. Now at extreme position the displacement y is equal to capital A, amplitude. The maximum displacement from the mean position is amplitude. At extreme position the displacement is maximum, that is y is equal to A. If you find the potential energy formula, half m omega square A square, in place of y if you write A, then we will get the potential energy half m omega square A square. This is the potential energy at the extreme position. So this is the maximum potential energy that can be obtainable. That means at extreme position the potential energy is maximum. That maximum potential energy can be taken as half m omega square A square. Potential energy formula, this is half m omega square y square, but maximum potential energy is half m omega square A square. So if you observe here, in case of kinetic energy, the maximum kinetic energy also half m omega square A square only. Maximum kinetic energy half m omega square A square. Maximum potential energy also half m omega square A square. So now let us discuss this later. Now the total energy of the particle, already we have discussed that the total energy of the particle is the sum of kinetic energy and the potential energy. That is kinetic energy expression already we got here, the kinetic energy formula, that is half m omega square A square minus y square. This is equation number 1, kinetic energy. And potential energy expression we got here, half m omega square y square. Then we have added the two. Kinetic energy is half m omega square A square minus y square, plus potential energy is half m omega square y square. Now if you simplify this A square minus y square, for these two terms we can apply half m omega square. We can multiply this half m omega square. If you multiply it, so we will get half m omega square A square, one term, minus half m omega square into y square. We will get two terms here, plus half m omega square y square is this term as it is we have written. Now this is minus half m omega square y square, and this is plus half m omega square y square. These two get cancelled. After these terms get cancelled, we left with the total energy half m omega square A square. The total energy is equal to the maximum kinetic energy is equal to the maximum potential energy. How it is? That means if you see this diagram, you can understand this. So let us consider this position is the mean position. So either side of the mean position, see this is extreme position and this is another extreme position. So this is the mean position. Either side of the mean position there are two extreme positions. This is extreme position and this is another extreme position. So now if you draw the kinetic energy curve and the potential energy curve according to the given values, now at mean position already we have discussed that the kinetic energy is maximum. At mean position the kinetic energy is maximum, that is half m omega square a square. At mean position kinetic energy is maximum. At extreme position kinetic energy is 0. Now let us take the values and here in the graph let us implement. At mean position kinetic energy is maximum, that is half m omega square a square is the kinetic energy. Now the kinetic energy is 0. The kinetic energy is 0 at the extreme position. Kinetic energy is maximum, that is half m omega square a square. It is maximum at the mean position. Kinetic energy is 0 at the extreme position. Similarly, if you see the potential energy is maximum at the extreme position, that is half m omega square only. Potential energy is minimum, that is 0 at the mean position. Let us discuss that also. That is at the extreme position, see potential energy is maximum half m omega square a square. At the mean position potential energy is 0. So at mean position or at extreme position, if we add the total energy, that is kinetic energy plus potential energy, half m omega square plus 0 gives total energy is half m omega square a square. At mean position kinetic energy is maximum, potential energy is 0, total energy is half m omega square a square only. But at extreme position kinetic energy is 0, potential energy is maximum. Here kinetic energy is maximum, here potential energy is maximum, but the maximum values are same, half m omega square a square. If we add these two in this, at this extreme position also the total energy is equal to half m omega square a square. That means at mean position total energy is equal to half m omega square a square. At extreme position also total energy is equal to half m omega square a square. That means total energy is constant. Energy neither be created nor be destroyed, but one form of energy can be converted into another form of energy. Here the total energy is in the form of kinetic energy at the mean position, and at extreme position the total energy is in the form of potential energy. That means if you see the graphs, so the kinetic energy is maximum at the mean position. This is the peak value, maximum value. And if you go towards the extreme position, the kinetic energy goes on decreasing, and at extreme position kinetic energy becomes 0. And this is the kinetic energy curve. And if you see the potential energy curve, this is the potential energy curve. At the mean position potential energy is 0. See, this is the 0. And as you are moving towards the extreme position, the potential energy goes on increasing. And here also towards this extreme position also potential energy goes on increasing, and at extreme position potential energy becomes maximum. So this is the potential energy and kinetic energy representation. So this is about the total energy of a particle executing simple harmonic motion. It is the sum of kinetic energy and the potential energy. Thank you.